Welcome back. Uh, I hope someone came back for the lesson, not only because we have a earphone here. But yeah, so just a recap, my plan was to sell you the planner code as a code that has all the ingredients that we need, and then actually show you that is not as good as we would like it to be. So to motivate a bit um, a new or a direction, strong direction in the field, that is the look and search for LDPC codes. And by this, even if the planner code is an LDPC code, I will mean today codes with more than one logical qubit, um, and how to do computation with them. So I'm going to talk about a specific class, which has been the first class in 2000, I don't know, 16. Now, this is going to be wrong, so I'm not going to cite the year precisely, of codes that had all the properties needed by the threshold theorem. And the planar code is actually an hypergraph product code, but it's not one of good type. It's not the best possible hypergraph product. We're going to see why. What is important is that, you know, we give up the locality of stabilizers, as in the picture that I showed you before, and we obtain all the other things that are needed to satisfy the assumption of the threshold theorem. So let's see how to actually build an hypergraph product code. So I hope you all remember this guy here. We have qubits on edges. It's just a lattice. This is the planar code. Now I'm gonna do something easy. So I'm gonna draw, instead of the two grids of edges, the vertical and the horizontal one, in a separate sectors. So easy. And instead of doing edges that remembers me of a lattice too much, I'm just gonna draw circles. So here, these 9 qubits represent the vertical edges, and these 4 qubits the horizontal one. So I'm just drawing planar code in a different graphical representation. And you can, let's try this game. Now I'm gonna, I don't remember what color was that. Oh, it was orange. Okay, so now I'm gonna select this plaquette operator. You can see that this plaquette operator has support on these first 2 qubits and this one, right? And if I translate the support on the circles, it's this one. Everyone agrees? It's just I'm coloring qubits according to the support of this phase operator. And if we look at this matrix here, that is the parity check matrix of the repetition code, if you remember, we can see that the support of these two guys is given by the first row, 110 is like 110, and the first column, 10, right? Okay, great. So I described the first stabilizer here as a combination of row and column of this matrix. Now, we're gonna try with another one. I can pick, if someone has preferences, I can pick the one you like most, but if not, this one. So this one, let's see. This one has support on the first row. So this guy and this guy, which are these two, and then these two, right? And if I look at this matrix again, it's easy to see that this is the second row and the second column. And what is true in general is that if I number, you know, the stabilizers by in row and column indices of this matrix here, I can find the support of each and every stabilizers with this trick. So this was 1, 1, and I took the first row and the first column. This is 1, 2, 2, 1. This is 2, 2, 3, 1, 3, 3. And you can see that with this game, I can describe all the stabilizers. And similarly, if I revert the column and the row index, so for Z stabilizer, we have this shape, let's say, right? X stabilizer, if we draw them, these ones are orientated in the other direction. So I'm gonna switch column and row indices. And what is important about this is that this is the only thing that I need. I need a classical parity check matrix. In this case, I took the parity check matrix of the repetition code. And then I'm gonna do 2 times the product of this tensor product of this parity check matrix. I decided not to go into the details of the chain complexes because I thought it was not very pleasant after lunch. And this is the only thing I need. So this matrix is 2 times 3. So I'm gonna have a 2 times 2 grid of right kind of qubits and a 3 times 3 grid of left qubits. And I can describe the support of the logical operators just like this. And as you can see, the only thing that is important is that then we can prove that we actually define in this way tell me. Sorry? The number of the square is supposed I don't
are they supposed to like mark first row and first column like 1 1?
Yeah.
Then that one should be 2 3 out, right?
Yeah, no, the other way. Sorry, you're right.
No.
So since it's up to 3, so the first coordinate is the column and the second coordinate is the row. So we can try with the 3 1. So 3 1 as support. And if I have put the indices wrong, that's something that I always do, and it's always the case. So 3 1 is supported here, here, and here, right? Which is here, here, and here, which is 3 1. Yeah, it's 3 1. Correct. Okay. And for X, it's the other way around, right? So it's gonna be the correct numbering. And okay, so what is important is that if I build something like this, I will have the commutation relationship that are respected. And the basic and more important information is that starting from a parity check matrix like this, I know that for one of the 2 kind of stabilizers, in this kind of Z, the support is going to be given on of rows on the left and on the right by columns. And with this trick, I can build a code and be sure that it's going to give me well-defined CSS stabilizer codes. So the problem with this is that we can, let's see an example that is not the repetition code. So in general, I can take any matrix, binary matrix, like this one is the parity check matrix of the admin code that we have seen yesterday with 1 more row because I wanted to highlight something here. And with the same kind of understanding, I can build a stabilizer in this way. So for instance, we have the stabilizer 1 3, which is going to be given by row for the X, by row 1 and column 3. And as you can see, for the X operators, I take the transpose of this relationship. So rows are going to be supported on columns, as happened here. So the row was 1 1 0 1 1 0 0, and this is exactly the support that I have here. And similarly, I transpose the column. And as you can see, stabilizers X and Z are always this kind of shape where they are supported on both left and right qubits. in one direction and the orthogonal and swapped. So I think the picture is clear of whatever description I want to say. And the logical operator, and this is telling me that this matrix, the seed matrix of the hypergraph product code, gives me the row span, the row image of this matrix gives me the span on the left qubits, and the column span gives me the support of the stabilizer on the right kind of qubits. As for the logicals, we can check that logicals are things we can find the basis of the logical operators X and Z, such that they are either supported completely on left qubits on a line or completely on right qubits. And X and Z are orthogonal to each other. So if the X operator goes horizontally, then the Z operator is going to go vertically. And what is important in that, you can actually check that the X and Z stabilizer, the identity commutes, because for instance, one guy of this type and one guy of this type, if they overlap, they're going to always overlap on one qubit on the left. And if that's the case, just because you can check with the indices of the matrix, they're also going to overlap on a qubit on the right. Or they don't overlap at all. So that's safe. And as regards logical X operator, for instance, this is a logical X for qubit 1. And as you can see, if we draw the support of the X here, they exactly overlap on one qubit. So again, we have the correct commutation relationship. And this is the only thing that we need. So we need this parity check matrix here. We need to know that the row span and column span describe the stabilizer. And then we need to know that the kernel, which is the set of vectors that are multiplied by the matrices is 0, describe the logical. And this is the only thing that that we need. And it works in general. So maybe this notation can look quite obscure because they've decided to skip the chain complex, but what is important is that you give me one, I will stick to the example where I only always use one parity check, which is delta A, which was delta in the previous picture. And I can build a code just with this trick by using the row span and the column span in the two different sectors and be sure that this defines a CSS codes. And what is important is that, the scaling, if I give and I use an input a good classical code, what I can obtain, this is what I obtain. So basically, the scaling is like n square root of n at most, and then this k can be as good as alpha n. So this is what I can do with hypergraph product codes, and it's easy to see, at least for the scaling, that this is the case if I take an input a good classical code. So the fact that the distance is as most square root, we can see that as in the case of the planar code, because I'm giving you a basis of the logical operator that gives me the distance or a bound on the distance. And I have a square grid of qubits, and each operator is supported only on one line. So the maximum size of that is surely square root of n, more or less. And, for the same reason, this gives me a bound of how many of those I can fit in this grid. And it turns out that if you use a good code you have this kind of scaling. What happens with the planar code that I told you is just, the hypergraph product code with the repetition code with itself, is that the repetition code is not a good classical code because, it's n, y, n. So the scaling, the distance, actually for hypergraph product code, the distance scaling is optimal because it's square root of n, as is the best we can hope for, but the rate is constant. So, and what I'm saying is that, we don't need to restrict ourselves to the repetition coding input. We can take any code, pull it in this product and they obtain a good family of codes. And this is interesting in general, like I didn't want to go through like the construction in those terms because all the good codes that we have seen comes from some sort of product. Here, I mean, basically when I have to describe the parity check, if H is the classical one, then one of the hypergraph product code is gonna have a form like a tensor product like this. And it's not, maybe it can seems a bit obscure, but what is important is that basically I am using a lot of more qubits than what is strictly needed. I'm gonna do a grid, and I'm actually only gonna use line kind of support for the stabilizer and the logical. And what is interesting is even the good codes that I told you exist, they all come from some sort of product that is basically used to ensure that you have the right commutativity relationship. So enough space so that when you combine the X and the Z stabilizer, they overlap in the right way so that they commute. And then maybe some quotient out, so removing some of the qubits that are not needed, some symmetries that you have created to actually obtain the good scaling. So hypergraph products are like the first example of codes that satisfy the threshold theorem and also give us a way to understand how we can do like logical operations or solve all the problems that we actually have in practice before scaling to the very good ones. And this is important because doing operations, if you only have one logical qubit, it's probably a different problem that if you have in the same code block more than one. And as long as we want only to share and protect our information without doing logic with our quantum computer, that's okay. We know that good codes exist, but what you will probably actually want to do is to run algorithms on your computer. So one problem is to understand how do you actually do operation in a fault tolerant way. And maybe I've touched on this a tiny bit, but at the beginning this morning, I told you that we take our qubit and the only thing that we care about is the algebra representation, so the poly X and the poly Z. So there are some operations that are the Clifford group operation that are easily described in this framework. And these operations are the one that maps poly into poly. So does anyone know what is that? Yeah.
Thank you. So just to recap, from the metrics that is designed in the code, or which you represent the code. So is there a way to understand whether there is or there isn't this anti-commutation or commutation relationship between the stabilizers? So if I have like a matrix and yeah, how can I see if that is respecting or it could be a potential matrix for a potential?
So any matrix will work, and that's because we can do it together. And in fact, the good codes, I am saying, if you want to have good hypergraph product codes in input, you have to put a good classical codes. A good classical codes are random. Gallagher, 1964, you take random matrices, that is going to be a good code. And any matrix works because basically I'm wasting a lot of qubits more than I need. I'm doing a grid instead of just using a line to ensure the commutation relationship. So the stabilizer X13 and the stabilizer 42, I don't think they're gonna overlap, but we can see that together. So I'm gonna draw stabilizer X13. So X stabilizer and X stabilizer are always gonna commute, so we don't care. Let's check the commutation relationship between x and z. So okay, so this is they overlap on the last qubits, and the overlap. So this is stabilizer 1, 3, the blue one. So 1 and 3 with the 4, 2. So 1, 2, 3, 4, and the 2. So now you can see that 2. Okay, so here in the row, in the big one, the one that are given by the row, I am looking at row number 1 and row number, I did this one, and row number 4. Sorry for that. And 2. This is not the correct one. This is 4, 2. No, I was okay before. Sorry. So the reality is that if you go into the picture with all the indices, that is way easier. But I decided to do that roughly, and now it's a bit of a problem, but it's okay. So it's 4, 2. Okay. So here I have row number 4 and row number 1. They overlap if I take the transpose of one and the other. If they overlap, since the support is on the qubit number 1, 2, 3, number 4, and here is number 3. So I have to look at the index. That is 1, 2, 3, 4. At this index here. So what I'm saying, that's I understand it was confusing, but the commutation is telling me, so here, if I have an overlap here, then I also gonna have on the other side at the 2, 1, 3 position, 1, 3. So I'm looking basically transpose and the other at the same indices on the same matrices. So if 3, 1 counting row column is 1, then it's going to be 1, 3 as well. And yeah, you can find that out. So the 4, 2, I also have to serve is not only, this is telling me to take row number 2 and putting that at the 4th position, right? So this is row number, the support of row number 2 at the position 4, and the support of column number 2 at the position. So it is giving me both at which height I have to put the line and what is the line that I have to pick. And if you look back, you have 1, 1, the same matrix twice. So it works for any matrix. That was not the cleanest index activation. Okay. So, okay. If we want to run computation on our computer, maybe the first thing that we can do is to do the Clifford operations that are the ones that preserve the Pauli operator. So map a Pauli to another Pauli. That's good because, you know, we are happy we can track the state of our qubits just by looking at what happens to their logical poly representative. Is also good on one side because, as I said, you can represent every poly as a symplectic vector, so 2n bits plus one phase that we don't care very much but about. So a Clifford operation can always be described just by tracking a basis of the poly and see where it goes. So for each poly, I see what's its image. And this is good, you know, we can write Clifford in an easy way on one side. This is also maybe less good because it tells us that we have an efficient classical representation for the Clifford operations, because we only need this amount of bits to describe a Clifford, while as for the general unitary, which is the general operation that you would like to implement on your quantum computer, that takes way more. However, you know, Clifford classically, you can simulate them classically, but are a good first example to study if we want to understand how to do computation on our quantum computer. So I hope everyone knows, but a basis for the Clifford is given by the Damard, S gate, and C naught. So the Damard, does anyone know what is the, where does the Damard maps the X, poly X operator? Is everyone familiar with this kind of things? And Z? S, any taker? Goes to Y. I'm just saying, you know, even if you don't know what the Clifford group is, I'm saying there is this group, these are the operation, and maps Z into Z, and then the C naught, we have seen that already, is the entangling gate, it maps X on the first qubit, next one, X2 is a 2-qubit gate, and X2 is the identity, and then Z1 same, and Z1, Z2, Z1. And, you know, as I said, these are operations that maybe we like, because as before, I was like, a qubit is given by some poly, and now we apply this kind of operation, and we only have to keep tracking the image of those poly. So that's the first step if we want to build a quantum computer. Then, you know, maybe we are not happy enough to have only operation on our qubits that can actually be simulated efficiently on a classical computer. So what is needed to obtain universality? So a finite set of operations that can approximate as well as we want all the operations. We need another gate, a gate that is outside of the Clifford group, and maybe you are all familiar with the block sphere representation of a qubit, being most of you physicists, and you know, this octahedron inside represents all the stabilizers, and the vertices are the eigenstates of the poly, so Z, X, and Y. And the Clifford are all the symmetries that are given by this octahedron. So basically, with the Clifford on one qubit, I can rotate the sphere, preserving the symmetries of this octahedron. And to convince you and give an intuition on why you need something else that is outside Clifford to reach universal for computation, this is how I like to think about. Let's suppose that you are on a lattice, you know, and you can just do left and right turn of 90 degrees. If you do, this is not very right angle, but it doesn't matter. If you do a random walk with only being able to go left and right 90 degrees, you're not going to be able to approximate any point on your plane. But as soon as you add to this, a turn that is not 45, but in, you know, a non-rational number, you can approximate any point on that plane. And that's the intuition why we need something that doesn't lie on these vertices of the octahedron to approximate any unitary rotation as like approximation with rational numbers of real numbers. And that's classically or very commonly is the T gate, which is the square root of S, or a rotation like that. And what we know is that, Clifford operation plus T gates, those are a universal set for quantum computation. So if we want to run algorithms on our computer, it's enough for us to find a way to implement all Clifford plus T operations in a fault-tolerant way on an encoded system. And we know that we can implement arbitrary algorithms on that. Since, yeah, I think to start, I will not dig into, it's very natural to start with the Clifford group because the Clifford group is described just as the stabilizer of the Pauli operator. So you may think that then it should be, it's also classically simulable. So you may think that then it's easy to actually implement the Clifford group on any code, but that's not actually the case. So I will just focus on the Clifford group because it already gives you an idea on what are the difficulties to perform fault-tolerant universal quantum computation. And to start with, I'm gonna introduce the color code. Color code is, should be your friend as the planar code is. It's the second best candidate around, and it's described like that. Qubits are on vertices. So I have 7 qubits here. And I have X and Z operators that are the same, which I mean that I have an X operator supported on this red face, but I also have a Z operator supported on this face, right? So I'm gonna have 6 stabilizers, and they are all supported on a face. So I'm gonna have, X stabilizers here, and a Z stabilizer on green, and then a Z stabilizer on blue, and the Z stabilizer on X. So basically what I'm saying is that in this code, each stabilizers on one of the face as its twin of the other kind, okay? And then, then I ask you, what happens if I apply Hadamard on all the qubits in this picture? So this is the action of Hadamard here. What happens is that, so to understand whether something maybe that's important, an important observation. So whenever you have your information that is encoded in a code space, to understand, you apply some gates to your encoded information. And to understand whether that's a valid logical operation, you want 2 things. You want to preserve the relationship that defined your qubit at the beginning. So basically, you want the identity to be mapped to the identity. So you need the stabilizer to be preserved. And then you want the pair of X and Z logical to be mapped to something else. So the image of X, we call it logical X, LX, and the image of LZ. But what is important is that the commutation relationship is preserved. So you want that as it was for the original copy of the logical operators, because this is what Clifford do, they preserve the commutation relationship. So if I apply Hadamard transversally on all the qubits at once, what happens to the stabilizer, the X stabilizer, the red X stabilizer? Yeah, it goes into ZZ. Is this a valid operation? it's a valid operation because ZZZ on the red face was a stabilizer as well. And you can check that this is true for all three or all stabilizers, so generating set of stabilizers, so it's true for all. Then, you know, I didn't draw the logical at the beginning, so I forgot to do that then, but I can tell you that a logical operator, a logical X operator is this one. And the logical Z operator is this one. So on qubits 5, 6, and 7. And as you can see, at the logical level, this is still true because I map X, logical X, into logical Z, and vice versa. So great. This is a more or less proof that Adamant on all the qubits actually implement an Adamant on the logical level on the color code. Now, let's clean this up a bit. S operators, you know, I'm gonna tell you, and you can do this by homework. I can apply S and S dagger. I decolor the vertex on purpose, so I'm gonna put S on the black vertices and S dagger on the gray one. And what you can see is that in this way, we actually implement the S gate. S and S dagger are necessary because, you know, the S gate has a phase and we want it to cancel out. So the S gate is this gate here. So this design is clear. So it's this gate here, and you want to, you know, X is equal to 9, XZ. And more importantly, when you map the stabilizer, you don't want to map X into IZ, but you want to map it into Z or something that is in the stabilizers. So since the overlap is always even, you know, X, S, and S dagger cancel out. What I'm saying is that the product of all these things on the face properly preserve the face as we want to. So very good. We have this color code, and we have Adamant and S gate. The logical qubit is only one. So, you know, the Clifford group was Adamant, S, and then C naught, but C naught needs 2 logical qubits. So we don't have it for now. Can we do the C naught? And as every CSS code with 1 logical qubit, whatever, we can actually implement a C naught in a very easy way. We take 2 copies of the same code, and then we do physical C naught between each of them. And you know, you can prove so 4 with 4, 3 by 3, and so on. And it's not difficult to see that this actually gives you a C naught between these 2 copies. And you know, that's the reason why the color code is very interesting. And then you may argue that I started talking about how good was the planar code, and now I'm going to the color code, but it's a small example that can show you in an intuitive way how you can potentially do operation when your code has only 1 logical qubit. And as I said, I'm only going to talk about Clifford gates, but you know, you can have a 3D version of the color code that has like a transversal T gate. And so with some tricks to go from one to the other, you can actually do universal computation with those. And what was good about the gates that I've showed you on the Clifford gate is that they are transversal. What does it mean to be transversal? So here, you know, there is 1 line for each qubit. That's what the picture represents. And the gates, I mean, these boxes here represent entangling gates, which means that if I apply this gate here, error can spread across all the qubits that touches this box. And a gate, you know, when I do a gate and a bunch of qubits, there are a few situations that can happen. So in the first situation, like if an error happens here, and then I have this box here, then where do you think the error can potentially spread with this box? Everywhere, yeah, everywhere, but yeah, in the first distance to this, the first one, then here and here. But then the problem is that I have this other box here that, you know, so one single error, if I do, you know, I'm only applying gates to do operation on my code. And if the gates that I apply are not, yeah, are put as in this example, one single error could spread to all the qubits in my system, which is not very good. In this second example, as you can see, you know, there is no untangling gate, so all the boxes only act on one qubit. So one single error, yeah, no, oops, can only spread to one qubit. So this is like best situation possible, as in the case of the Adamar gate, right? We have seen that. It's a symmetry of the code. I apply that, I do an operation, and error cannot spread. And then, you know, there is an in-between kind of situation. That is where I have a partition of qubits and gates that are transversal inside the partition. So, you know, this error here could spread to this qubit and this qubit, but nothing else, because then the other entangling gate is between other two that has not been touched. And, you know, this is maybe the case that we're gonna focus on, and this the case that can give us something, because of course, in order for a code to have like this kind of gate, it's very restricted, right? And if you want to reach something more, then there is this probably looser definition of transversality that is the one that can give us more computational power. While this, of course, you know, is very clearly not fault tolerant, no matter what you do. Okay, so I said, okay, Clifford plus D is universal. I'm gonna focus on Clifford only because it's better. Then, you know, the easiest way to be sure that something is fault tolerant is to look at transversal gates. And you have seen why that is the case. The problem is the other disclaimer is that not only I'm saying I'm only talking about Clifford, I'm saying I'm talking about transversal gates, and as Philip mentioned in a slightly different setting yesterday, we well know that no code that protects at least one qubit from errors has a universal set of transversal gates. So it's the so-called Einstein-Niels theorem. Then we have other better bound and understanding of what are the constraints for a code to have a set of fault-tolerant gates transversal-wise. And so maybe the question is, why should we care about this? And, you know, we start seeing some experiments based on platforms that are not superconducting qubits. In this example, cold atoms, but ion is the same, where you have platforms that have more mobility. You can maybe pull all your qubits in an area and do a transversal gates on a bunch of them. And that's good because we can start seeing actual implementation of transversal gates, logic done with these methods. So it's still interesting. And also it's the cheaper way you have to do fault tolerance logic. So take your code, you hope that it has some good transversal gates, and then you find other way to do the rest. So easy, it's easy to see that transversal gate is fault tolerant. Just talking about Clifford is not, we know that it's not universal, so it looks very, very easy, a problem that is already solved there. But actually, I think it's very important to appreciate what is the real difficulty of having transversal gates in a code that encode more than one logical qubit. So let's suppose that your code is a box. So you have a code with one logical qubit as the planar code. So you take your box and you protect your qubit, this octahedron here, and you put it in a box. And on the other side, you have codes with more than one logical qubit, and you put like 3 in the same box. Now, doing a transversal operation, you can think is like taking a bucket of paint and put it in the box. What happens, of course, is that, you know, if your box has 1 qubit inside, you're going to color that qubit of that color. But if you just throw a bucket of paint in a box with a lot of qubits in it, they're going to all be colored with the same color. But what you really want to do when you want to implement an algorithm is to be able to address each logical qubit with different operations, right? What I'm saying is that, you know, maybe you want qubit number 1 to have an X on it, and qubit number 2 to have an S, and the other qubit to be the other mark. So the problem with using transversal gates on codes with more than one logical qubit is that we need to find a way to address them one at a time. Because it's very likely that if you have your code space that encode your information and you're applying some global, as in product of Clifford operation or whatever operation, it's very likely that you're going to act on all of them. And this takes away some of your addressability power that you have. And yeah, so that's, you know, the main difficulty with finding transversal gates for codes with more than one logical qubit. And, you know, in general, doing logic with LDPC codes is not, we don't have a recipe that is, you know, the major to go for now. And in this slide, I've put some references, and on the left, you know, we have general purpose kind of strategies that works for any CSS code, for instance. And on the right, there are strategies that works only for some kind of code. So that exploit the symmetry of the code itself, like for instance, you know, the color code that has a lot of symmetry, sex and Z stabilizer are the same, and are tailored on the class of codes and on the symmetry, and tell you what kind of operation you can do. And, you know, the general ones, of course, maybe you spend more time or more space, and maybe on the right one, they are not as general, but maybe are the best for the class of codes that you can see. However, you know, it's not, on one end, for the planar code, there are, I would say, standard way people will consider to implement a full set, universal set of fault tolerant operations. For LDPC codes, that's not clear. And one of the problems is exactly the addressability of single logical qubits inside the box. So, you know, you apply an operation and you act on all of them. But, you know, to really exploit the fact that you have more than one logical qubit in it, you need to be able to address and do that. And so I would like to quickly show you like a few ideas on how you can apply the same idea that we have seen on the color code on hypergraph product codes. And this comes precisely to the combination of the color code and the planar code. So you can prove and write that you can fold a copy of the planar code and obtain 2 color codes. As you know, some Clifford equivalence, it doesn't matter, but there is a close relationship between color code and planar code. And, you know, as I said, the planar code is actually an hypergraph product code. So the next question is that, can I do some color code kind of trick on planar codes and hypergraph product codes in general to obtain the same kind of operation that I had on the Clifford, on the color code? The answer is yes. You can do that on hypergraph product codes and on other codes as well that have these kind of symmetries. And I will show you just as a, yeah, just to study a bit more what is the structure of hypergraph product code. And, you know, without going into too much details, like I started saying you take a parity check metrics like this, and then the logical are described by a basis of the kernel. So I can tell you that these four guys here are basis of the kernel of your parity check. And, you know, it's not, you can find a basis that is nice, as in this basis is nice because look, here are all zero below, all zero below, all zero below. So I have all zero below the stars and on the right as well. So next to each pivot, I only have zero. So whatever, it doesn't matter. I want to show you that sometimes you have to exploit, like to see what are your transversal gates. You need to find a particular structure on your code. And with those, you can understand what are the gates that preserve the code space. And you know what is not very, yeah. The only thing that I want to point out is that this pivot here that I've highlighted, you know, they all have support number. So this is the third one because the pivot is on row number 3, 5th, 6th, and 7. And what I'm saying is that I can describe the logical code space just by doing the product of these two numbers. So what I'm saying is that I can write each and every logical operator, uniquely identify those by the pivot that is going to be the qubit where X and Z operator overlap. So what I'm saying is that, you know, if I have 4, this is the kernel of the repetition, whatever, I have 16 kind of combination for pivot. And in fact, you know, and this gives me the logical space of hypergraph product codes divided into 4 sets, I will say. So the logical operators that are supported on the left, the one that are supported on the right, the one was pivot lies on the diagonal, like for this logical here, this is a logical X, and this is the corresponding logical Z that are anti-commute. As you can see, they are the same column and row, and their pivot, they overlap, lies exactly on the diagonal. And similar, you know, and this is, I took twice the same vector, so I call this logical operator 3, 3. And then, you know, I have 3 and 6, and I can have this kind of configuration or the symmetric one. And what I'm saying is that actually in an hypergraph product code, you can divide the logical as the one that are on the diagonal or the one that are symmetric across the diagonal. For instance, these guys here with these guys here. If I fold along the diagonal, they're gonna be the same. And as you can see, the support of the Z is equal to the support of the X for the other one. So there are very clear symmetric relationship between these two. And this relationship tell us how can we do some logic. And you're gonna find out that we can actually implement the same gates that we've seen on the color code with some drawback that, of course, you are maybe expecting if you remember the box and the bucket. So without going into details, I hope that this is clear. So here are the real stabilizer of an hypergraph product code. So the blue one, X, are vertical on the left, and the Z one are the other way around. If you apply Adamant, what happens is that you have something that is, you know, almost okay, but the color is off. So to fix this and preserve the stabilizer, we just fold across this diagonal and then swap the qubits that are identified in that way. So this one and this one, you know, just across the diagonal. And if we do this, we find that the stabilizer is preserved. So just by folding and swapping, I preserve the stabilizer. And it's not difficult to see that in the same way the logical are exchanged. And what happens is that with this operation, on a code with more than one logical qubit, I've done Hadamard on the diagonal qubit, on all the ones that were represented by the pivot on the diagonal, and I've done Hadamard and swap between the one that were this one and this one, the associated one, at two indices. And this is exactly, it's exactly Hadamard everywhere, what I did for the color code. And in the similar way, I have kind of an S-gate. Before with the color code, I have colorability, so I applied S and S stagger. Here, I have to do something similar, and is one of the gates. So that was transversal gate. I'm just applying Hadamard, so we are in the picture where these were the line of qubits, and these were the gate, right? Fully transversal. Fault tolerant for free, no error per spread. And then, we have the intermediate picture that I showed you before. When I partition the qubit in sets like that, and I know that in this way, one error cannot spread to more than two. As you can see, there is one only, but it's okay. And in a similar way, again, by exploiting the symmetry, the fold symmetries of the code, you can apply a gate, see that it preserves the stabilizers. I don't want to lose time to go into the detail. And basically, you can obtain a gate that doesn't look very nice on one side. Basically, I do a bunch of S stagger, and CZ gate on the physical level. And on the logical level, I'm going to have S gate on the diagonal logical qubit that are on the right, S stagger on the left, and CZ between pairs. So I see that between these two guys here, I see that between these two, and so on. Okay. And this is, good enough, but and so on, the other one that I've played. And this is exactly right what we were expecting at the beginning. So I'm applying physical gates everywhere, and I'm actually acting on all the logical qubits. And this is, on one side, this can be, it's a very cheap way to do logic, because you don't need for the machinery to ensure that it's fault tolerant, but you don't have addressability. And in fact, the gate that I obtain, here I have, it's not very clear. It's not in the nice Hadamard S and C naught. Like, what should I do if I want to do a C naught between qubit number 1 and qubit number 4? So that's not maybe the best thing you can do to do logic, but exploiting the symmetries of the codes can anyway help you understand how to parallelize your algorithm and write that down so that you can do the maximum amount possible of operation in parallel on more than one logical qubit. So even if this is not the best strategy to actually do gates, knowing the symmetry of your codes and understanding how the logical basis is represented and what are the relationship can anyway inform you on some compilation aspect. So for instance, here, I was, yesterday, Philip mentioned the Tori code is the same as the planar code, but we have agreed that is the same at the left of the right. It doesn't matter very much, but you have, of course, the same kind of symmetries. Is again an hypergraph product code with square matrices. And what you have is that you have some logicals that are supported on one grid, some other in the other. And you can do a CZ between two logical operator in the same code block by doing a lot of CZ in between the qubit in the support. So here in this picture, I want to do a CZ. This is what is representing between the black logical and the pink logical. And to do one, you can prove that you can do in 4 steps. And the first one is doing a CZ between the 2 yellow and a CZ between the 2 green and the CZ between the 2 blue and so on. So what I'm saying is that even a nice basis tell me that I can actually do this in D time steps. And these 3 CZ I can do in 1 round because I'm not touching the same qubit more than once. So even if this doesn't tell us how to do logic per itself, it can maybe inform us how to compile the better. And for instance, here in this picture, what I'm saying is that I can do all this CZ, pink with pink, blue with blue, and so on in one go. So if I have to do 4 logical CZ and I have like a nice disposition of the basis, I can do that in 1 time step. Yes. So this is one of the setting where we could use that kind of symmetries, and but still what is missing is the addressability. So one method and one topic that lately is gaining more and more attention is to try to use another classic method from the planar code this time, which is lattice surgery, to do computation on LDPC code in general. So I don't want to dig too much into that. I just want to say another way to implement the Clifford group is to use measure Pauli operators, product of Pauli operators at the same time. So I don't know whether you are familiar with this kind of picture. What I'm saying is that if I want to do a C naught between the control and the target like this, what I can actually do is I can prepare an auxiliary qubit in the plus state and then do this circuit. So measure ZZ, XX, and then you can prove that this guy here actually implement a C naught between the control and the target. And this lattice surgery is exactly what is used. Like, I don't know the name of the person who wants to do the quantum computer with the planar code, which is something a lot of people want to. But this is what actually like the proposal that is used to do fault tolerant computation in a planar code architecture. So basically, you have your patches of planar code 1 and 2, and then if you want to do a C naught between the 2, you actually do this lattice surgery protocol when you measure joint Pauli operator between the 2. And yeah, so the problem is, let's suppose that you have your computer that is made with a lot of patches of the planar code. Then, if you want to do a C naught between code 1 and code 2, then you measure the joint operator here and it's easy. The problem is that if you want to make a logical C naught between qubit 1 and qubit 8, then, it's a bit more difficult. Either you have to swap a lot or you have to add things in the middle to measure and connect the 2 of them. But what is more relevant about this is that, as you think, as before, whenever you do a logical gate with this method, one only error in the measurement of ZZ or XX can actually give you the wrong logical measurement. And I don't want to, go, maybe I should go into one or two details. So what you do if you want to measure ZZ operator on these two guys with lattice surgery, this is two planar code, you add two qubits in the middle, like this, and then you measure all the, let's do orange, all the Z operator, and you also measure the new one. These are the new ones. This guy here, this guy here, and this guy here. And now you can see that, if you do the product of all the base operators that you had before, plus these two, plus these three in the middle, the product of all of them is actually this times this. And what happens is that, actually one single error here can make you infer the wrong measurement for the operator Z1, Z2 logical, which, could translate in you badly doing a CNOT. So what is actually done in this setting, instead of doing one round, as it happens for actually error correction, when you just have to infer a recovery operator, you need B rounds of measurement so that you are confident enough that your stabilizer results are correct. So the right picture for lattice surgery is not the one to have like just a planar, you have two planar code and you measure in the middle, but you do that in 3D. So you also build your code in time and you repeat this 3 times, which is quite expensive. So when and lattice surgery on LDPC codes, has the same problem. On one side is more difficult because again, we have to be able to address single logical qubit that can be expensive. The trick for now is to basically teleport one of the logical qubit state into a planar code and then use the planar code to do logic. No matter what, still we need the round of error correction. So, transversal gates are not perfect, lattice surgery either. And this maybe give us time or suggestion to think about another problem beyond the one of logical computation, which, put together the coding and logic as well. So the problem is that in error correction picture with stabilizer codes, what we do over and over again is syndrome measurements, basically. So we could use those to for the coding purposes, or we could use those to do lattice surgery and then logic. But in both cases, what so far I have tried to do is just thinking that they were correct. But we cannot release a quantum operation as well, so that's prone to error as well. And yeah, as I mentioned, to contain this problem, there are two kinds of proposals. That one is just to repeat the measurements and have like a repetition code over time. And the other one is to use something else that we're gonna call a single shot code and decoder. So what I'm saying is that in the single shot picture, I'm asking you to find a code and the decoder also, always together. And, if before I wanted to give you measurements and I want you to give me back a recovery operator, this time around, I say, look, I give you some measurement. I don't care about you cleaning up all the errors that are on the system in one go. I just ask you to keep the error under control over time. So do not find a recovery that completely remove the syndrome from the system, but just make sure that after 10 100, whatever, time steps, the error on the system is low enough so that it doesn't accumulate in a tragic way, creating a logical gap. And the idea of what we should look for to build single shot code and decoder can be taken by the Ising model in 2D. Here, this time I am putting bits or qubits on faces, and I'm measuring checks. This is like classical thing. So the checks are the edges. What I'm saying is that in this picture, the qubits are this gray thing. And what I'm saying is that if this bit flips, then all the checks on its perimeter are going to be lit up. And if I am in a situation like this, what happens is that very clearly there is a relationship. So let's suppose that you don't see the gray bit, you only see the red bit, the syndrome, right? So problem is that you know that the correct syndromes, the one that comes from error for real, can only be closed loop. So if you see this guy here, you very clearly know that that's a measurement error, because it cannot come from, there is no closed area that has this as its boundary. And similarly, if here, if you measure and you have this red loop and the loop is not closed, the most likely thing that has happened that this is a measurement error and actually the loop was closed like that. And yeah, and this is the idea behind single shot. What I mean is that you have a system where you have kind of an understanding between the relationship of the error itself and the syndrome. And if you have something like this, then you can, under some noise assumption, correct for errors without repeating the measurements. And what is like a property that encodes this information, like it can be seen by the 2D Ising model very clearly, but what is important is that, as I said, there is a relationship between the weight of the error and the weight of the syndrome. So in this case, error is the area and the syndrome is the perimeter. And whenever you are in this kind of situation, when the weight of one grows with the weight of the other, basically you can find ways to keep your error under control over time. And yeah, I will not go into the details of that. I think we had enough, but oh no. But the important thing is that this is very relevant both for error correction and for logic, right? Because at the end of the day, like stabilizer measurement or that kind of operation are going to be done over and over again. And we're going to need, in a way or another, to rely on those results. And, we can trade off. Yeah. So this is just the model that I'm presenting. I'm telling you, like, I'm putting bits on the faces, and the syndromes are all the edges. So proper errors are all closed loop. This is not in general what is needed for a code to exhibit single shot properties. What is needed is this relationship. It's only this relationship. So the weight, this is the relationship that is needed. The weight of the syndrome grows, is not important, can be a polynomial function, whatever, grows with the weight of the error. So this is what you want. It's just have a relationship such that the weight of the error grows, the width of the syndrome grows more or less that. And that's, one example. It's the boundary. Um, and, one topic and one question that people ask themselves quite a bit is how can I, so we know example of codes that are single shot and maybe that was interesting, but it doesn't matter. We know example of codes and decoders that have this single shot property. So, but we don't know how to devise a protocol in general that is single shot. Like we don't know how to do lattice surgery with number of rounds that doesn't scale with the distance. And again, the setting is a bit different because in error correction, classical error correction or whatever, we want the decoder to take back the system into the code space. While it's here, we want the system and the algorithm itself to have a sustainable threshold, which is a concept maybe that is worth looking at. What I'm saying is that whenever you have to study the fault tolerance of your protocol, you need to have surely a definition of what is your noise model, but also what is your definition of success. So what does it mean for you to have a successful run of your algorithm? So in the single shot setting, what we look at is this quantity here, which I think it's worth looking because it's different what we had before. Before we had a threshold and we're just saying, the bigger the system, the less error. Here, I want to be sure that if I grow the number of rounds that I do of syndrome extraction in my system, so if I keep going with my computation long time, then the threshold of that system with n round, but while when I'm looking at the system in time, is still positive, right? So the limit as I grow n, I'm able for each number of rounds, so no matter how long I want my system to survive for, still I can keep going. So which means that at each time step, maybe I will have not cleaned the error for all the system, but well enough for the information to be stored. And yeah, and this, it's interesting, maybe particularly for physicists, because, we know what is a sufficient condition for a code and a decoder to have single shot properties, which is basically this thing that the function of the weight of the syndrome grows with error. And we know that this is sufficient, but we don't know whether this is necessary. And as we know, how to build self-correcting quantum memory, maybe some people have heard about that, but we don't know the close relationship between like energy barrier and single shot. So if a code has a single shot property that has an energy barrier, that maybe is a word that is familiar to some of you. But it's more or less like still of an open problem to understand precisely what are the necessary conditions for a code to exhibit this kind of property. And so the next question is, if instead of staying in the code picture, if we are willing to look at our computation and algorithm as a whole, as in the case of the lattice surgery, so to do logic as well, what are the minimum requirements or what is best we can hope for in terms of trade-off between space and time. So maybe, of course, I'm willing, to use a bigger code, a bit less efficient, but that allows me to gain in the time steps that I have to do in order to ensure fault tolerance. or maybe the other way around. And I think, the problem of understanding how to do logic when you have more than one logical qubit and what is the best efficiency bound you can have to do logic with as few round of error correction as possible. So maybe in a single shot setting, or maybe something that scales the square root of this or something like that, is one of the most interesting problems that are around for now. So I think, yeah. To conclude, just I think what is another direction. So we have, yeah. I hope I convinced you that we should go beyond the planet code. And also convince you that you should use your code to do logic as well. And that it's not easy how to do logic with codes with more than one logical qubits. And I think that's, a fun problem for math people or physicists or computer scientists, because yeah, transversals is easy, but when you have more than one thing in one box, that's very easy that you're gonna act on all of that. And then, that's something that is, what is the real trade-off between space and time when you have to do logic and the code. And the problem on what is a necessary condition, for instance, to have a single shot code where you can just go on for your computation without being perfect, is not clear. And to conclude, what is something that a lot of people are keen and keener to look at is, instead of looking at this stabilizer code picture as like you have a code and then you do logical operation, then you measure your syndrome and so on, is something that maybe puts together all of this problem, which is like at the end of the day, you're going to run a computation, you're going to have an algorithm, and you're going to compile it. So you're just going to have, let's stay with clipboard, but a very big circuit that goes from the beginning, which is your non-encoded state, to the end, that is your result. And in the middle, you can have a stabilizer code here, then you can do some logic, and then you can have another stabilizer code here that is a bit different. And but at the end of the day, you don't understand how many things changes in the middle. You just care about the fact that the result that comes out in the end is reliable. So probably looking at the whole picture, even when you look for the trade-off between space and time, and is the way to go. And I think we can learn a lot how to do logic efficiently, because we could split the cost of our correction and logic across the whole algorithm. And we don't really care whether we are using an hypergraph product code or a color code or whatever. We just care that at the end of the day, the cost of running our algorithm is as low as possible and the result is reliable. So yeah, I think with this, I hope I've given to you some idea of what people are thinking about in error correction world. And yeah, I think it's coffee time.
So just before coffee time, we have another 2 minutes, so that leaves room for a couple of questions. Yes. Hello. Thank you for the very interesting lecture. I just wanted to ask, are you aware of any papers or algorithms that implement quantum error correction successfully?
You mean experiments?
Yeah.
Sure. Okay, so as I said, you should define what successful means.
Well,
yeah,
you said that we would need big number of qubits in order for there to be actual any correction.
yeah,
in the terms.
yeah. No. What I'm saying is that there are a lot of companies or people that are trying to showcase that their qubits work well and they can actually do error correction. So I think a couple of days ago, there was that Google paper, maybe a week ago, where they implement like a planar code of distance 7 and one of distance 5 and 3, and they saw better suppression in the distance 7. But you know, the number, so what I'm saying is that a successful experiment? Yes. Is that a completely successful showcase of error correction? It's very tricky because it's always like a finite size. It's very close, saying that you have suppressed, and yeah. But I can point at you at some papers. I don't know, maybe if you have your favorite experimental results with error correction, like Quantinuum has done a bunch with also logical operations. Google, no logical operation, only error correction cycles.
Okay, thank you. And my second question is, what, how would you, since I'm not really an expert in quantum error correction, how would you go about it? You want to personally try and do error correction on an algorithm or a circuit that you have? Would you start, for example, a Bell state? It's an ADAMA gate and a CNOT. Would I just map my qubits to logicals and then do the operations, or how would that process work?
Yeah. So as I said, I think that maybe a better approach will be to like you tell your algorithm and then decide what kind of encoding you want. What is true is that platforms of today are very, very limited on what you can and cannot do operation wise. So
okay, thank you.
Another question, maybe. It's over there. You are making me walk too much.
So I was reading a paper about quantum Taylor codes for like some, I don't know, defined noise channel. So where they were optimizing the stabilizers for having like better filters to represent like noise and so on. Can you do something like that also with the hypergraph code?
yeah. So I'm not sure I understood what kind of work you're referring to. So if it's like bias tailoring or just
bias tailoring.
yeah, you can. Usually you can. So if you want to tailor your code for noise, you can apply some local Clifford rotation, and you're gonna increase like the Z distance against the X distance, and that is something you can do with CSS code, I think.
Is there some property maybe of in the method that you show that can like represent certain properties against bias?
Yeah, for sure. Like you can basically, when you want to tailor your code for the noise, what you're asking is to have a distance that is way bigger the Z distance and lower the X distance. So you cannot have both of them too good, but you can pick two different matrices, one the transposes one the other, and make sure that you have that. But you can locally transform your code to ensure that kind of property is. Yeah. It's surely something you should be thinking of.
Okay, one last quick question.
So you showed us with the color code that you can do transversal differences operations. We didn't really talk about the T gate. I just wanted to clarify, can you do a transversal T gate?
Not with that color code. Okay. You can do it with a 3D one.
Okay. Can you also talk a little bit about, people tend to say the T gate is the hardest to implement, it's the most expensive. Can you say a little bit about why?
So surely there are, per se, I think, I don't know whether the T gate in a lab is the most difficult to implement. I'm not sure about that because it's a dead rotation, and I have the feeling that people are happy doing that more than they are happy at doing CNOTs or stuff like that. The thought about the fact whether it's expensive or not is that I think there is also coding picture where we know that, the Clifford gate, we can simulate that classically. And if we have to keep track of the state of our qubits, we have to keep track of the poly that represent those. And basically, we can just in software update a lot of the Clifford thing. And the problem is that, and we can defer the error correction procedure till we don't apply a T gate. Because before, if you have a circuit with a bunch of Clifford and at some point with a T gate, before applying that T gate, you have to be sure of what is the state of your qubits before. So your error correction up to that point has to be ready. For that reason, when you have Clifford, you can delay your computation even if you're a classical computer helper that tells you about the state and the correction, can be slowed. But when you apply T gates, you need to be up to date. And also, as I said, Clifford is classically simulable, so the amount of T gate in your algorithm gives you also like a understanding on how some quantuminess, whatever.
Okay, so with that, we can conclude Dr. Armanda's session. Let's thank the speaker again. So now we have another coffee break, which will then be followed by our last perspectives panel. And in the meantime, please look at the WhatsApp group because Jake has kindly given us a form for you to fill afterwards to give us some feedback.